if compared, then the longer column, as expected, will have higher column separation efficiency. With increase in the length, there is increase in the N, increase in column separation efficiency. But we also cautioned ourselves that we cannot increase the length of a packed column beyond certain limits, otherwise it will lead to increase in the analytical time. Correct? Now I am making a statement that although capillary column lengths range from 25 to anything up to 100 meters, in addition to increase in column separation efficiency, there is decrease in the analytical time. And my question is, how do you explain this? Because learning gas chromatography is not just going through the slides, but asking yourself these questions. That practical observation is very simple, that although length of the capillary column is about 100 meters, but still there is no loss in analytical time, and there is increase in the column separation efficiency. Why? We have still 5 minutes. You get my question? Yes or no? Okay, my question is, that in capillary columns, the length varies from 25 to 100 meters. And generally we have said earlier that if the length increases, the analytical time increases, and therefore we optimize. But in the case of capillary columns, although length increases, the analytical time doesn't increase compared to the packed column, and in fact there is increase in the column separation efficiency. What could be the reason? And if you answer this, then I will say that yes, you have understood the theory of chromatography also. Any volunteer? Yes?
Number of theoretical plates
is increased, therefore column separation efficiency increases. But what we said earlier during our discussion, that we have to optimize the column length, otherwise the analytical time will increase. In this case it doesn't happen that. Capillary column, although you increase the length, the analytical time is not suffered. You get still reasonable analytical time and very high column separation efficiency.
Sir?
Yes, yes.
Eddy diffusion is avoided?
See, please remember, in a way you are right. What is eddy diffusion to do with? Eddy diffusion has to do with multiple path flow, right? Now you are right in saying that there is no question of multiple path flow because the central part of the column, capillary column, is a tube. So there is no hindrance, all solutes can travel in straight line. But my question is, in reduction, in not reduction in analytical time, eddy diffusion is just reduced, I mean almost negligible. Yes?
The strength of mobile, eluting strength of mobile phase uses.
Sorry, say that again.
The eluting strength of mobile phase is more. The mobile phase used.
Now, in the mobile phase used in gas chromatography is an inert gas, like nitrogen, helium, argon, etc., which does not play part in separation process. Yes?
Sir, although the length is increasing, the volume is decreased and because of the capillary action.
Yes, sir, you are right. See, you have to think of the dimension of the column also, diameter. And therefore, the diameter compared to the packed column is so small that in fact the column separation efficiency increases because of decrease in the diameter, increase in the length, and because of the decrease in the diameter, the time taken for flow of solute molecules along with the mobile phase through the 100-meter length is not that big. Right? Now the next thing is, where are the applications of these capillary columns in practice? The applications are mainly in the field of separation of solutes which have very close boiling points. In fractional distillation, we do that, but it takes a very long time. In gas chromatography, those gaseous solutes which have very close boiling points can be effectively separated using capillary columns because the length is very high and therefore there is enough time for solutes to get separated from one another. And one of the best applications of capillary columns is in petroleum industry. You know, petroleum fractions contain a large number of hydrocarbons with very close boiling points. And if you apply the capillary columns there, then you can separate the solutes, gaseous solutes having very close boiling points, and you get very sharp results. Let us go back to our discussion here, and that is, we have already said that process of separation can be considered as a series of partitioning. And the affinity of liquid phase for a sample component determines the length or time each individual component will remain in the solution, that is on the column. And after a number of partitions, the various solutes will separate into discrete bands. So what we have discussed, general chromatographic theory of separation is applicable in gas chromatographic separations as well. And the most volatile solutes usually pass through the column first, and the least volatile or highest boiling solutes emerge last. Because we have said that generally, not in all cases, but generally, the volatile solutes get separated depending on their boiling points. So the low boiling will first, and then the middle boiling, and then the highest boiling solutes. This, okay. This is again an animation. Yes. Yes. Just hold on. Next. 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 So at 0 minutes, you can see all the three solutes are forming a narrow band. But as they proceed, after 1 minute, their separation starts, and in a hypothetical case, after 2 minutes, they are separated into three individual bands. Now, there is no rule of thumb per se as to which liquid phase is best for your type of sample. But then, the right selection is based mainly on experience and trial and error. Because we have seen yesterday classification of non-polar, polar and spatial stationary liquid phases with some examples. But that was a very approximate. There are hundreds of stationary liquid phase available, and to choose the best between them is a matter of experience and trials and error. but the theory behind it, the knowledge of the theory behind it definitely helps you optimize the conditions and selection of liquid stationary phase effectively. Next, basic requirements, we have said it's an absolute solvent. You can skip this because we have already seen this. Next one. We have also seen this, that the selection of the liquid phase depends on the composition of the sample and the type of solutes will determine the type of liquid phase that you choose. For example, hydrocarbon compounds are best separated with a hydrocarbon solvent, that is liquid phase. And paraffins are best separated by squaring a long chain hydrocarbon. And polar solutes like alcohol are best separated by polar liquid phases. Just have a very close look at this particular plot. Same two solutes are there in 1, 2, 3, 4, 5 chromatograms. The only difference we are bringing from top to bottom is the top one is 30% liquid phase, 20% the K dash has decreased, retention times have decreased, and further with 5% liquid phase loading there is further decrease, and 1% liquid phase loading further decrease. So it shows direct effect of liquid phase loading on the separation and retention times. And I think the third picture is good enough for us. With 5%, 1% we are getting overlapping peaks and we are not interested. So this knowledge of theory is important, that liquid phase loading and the retention times and also the effect of K dash on resolution. Now separation factor, we have seen alpha in case of general theory, that we have defined separation factor as ratio of K2 dash upon K1 dash, where K2 dash and K1 dash are respectively the capacity factors of the second and the first peak respectively. So here also, relative positions of solute peaks on a chromatogram will determine the ratio of that will determine the separation factor, or relative retention is expressed as the ratio of retention times. Thus, alpha is determined by the respective distribution constants Kc, that is K dash in our early case, of the solutes in the liquid phase at a given temperature, because it is gas chromatography, we are specifying temperature, a given temperature. Remember how we defined yesterday Kc? Number of moles of solute in the liquid, that is stationary phase, to that of mobile. So is it not equal to Ns upon Nm that we thought? Exactly. So Ns upon Nm is K dash, correct? And K2 dash upon K1 dash was our separation factor. So here Kc2 by Kc1 will be the separation factors between two neighboring peaks in gas chromatography at a given temperature. So given temperature. See here. Here the liquid phase loading is kept constant throughout. What is changed is temperature. 30, 40, 50 and 60. Yesterday we did say that as temperature increases, the concentration of the solute molecules will increase in the mobile phase and retention time will decrease. See here, retention time in the fourth case is the minimum. This also, if you look at this in the reverse way, from 60 to 20 to 40, you will see that with decrease in the temperature, the resolution improves. In the fourth case at 20 degrees, almost separated, but still there is an overlap in the base. That overlap decreases, further decreases, and of course with 30 degrees, it's further decreases, but then it's waste of time. So the point to be driven home, or points to be driven home with respect to change in the liquid phase loading and change in the temperature in gas chromatographic separations are: number one, as the temperature in this case increases, retention time decreases. But for better separation, we did say yesterday that decrease in temperature is favorable. This is what is shown here. With respect to liquid phase loading, as liquid phase loading increases, retention increases. And therefore, liquid phase loading should be that where retention time will not be very high, at the same time resolution will be baseline separation. So in the earlier case we said 5% of liquid phase loading was satisfactory. In this case 50 degrees temperature is satisfactory for our better separation in gas chromatography. Now this is something of a very special stationary phase, which is called as Chromapack. Chromapack is a brand name. You know that Crocin, is it the name of the drug or is it the brand name? What does it contain? Paracetamol. Is it not? So Chromapack is like Crocin. And therefore it's a brand name, but there are Chromapack stationary phases used in gas chromatography, and there are variety of Chromapack packings from which we can choose, and that is why we have made mention of Chromapack. Next. So Chromapack column contains only the porous polymer beads screened to a definite mesh range. No liquid phase or solid support is used. That is the speciality of Chromapack. The solute molecules position directly from the gas phase into the amorphous polymer, which is called Chromapack. Next. Now there are 6 types of Chromapack materials: P, Q, R, S, T, and N, depending on their application, practical application in gas chromatography. Chromapack N has been developed for separation of formaldehyde mixtures and for the separation of acetophenone and ethylene. Specific application. So if you have this application, don't think of what column to be used. It's ready-made available material, Chromapack N. And all beads are available in various particle sizes ranging from 50 to 80 mesh to 150 to 100 mesh, and all polymers are stable to 250 degrees except Chromapack T, which is only up to 200 degrees Celsius. So we have made a special mention of Chromapack because the 6 varieties or 6 types of Chromapack materials, which have no liquid phase coating, but they have specific applications, and if you have those applications at hand, blindly you can just select R, P, or Q, or R, or S, or T to one end. Right. Now Chromapack is used primarily for efficient separation of a wide variety of relatively low molecular weight solutes. And Chromapack column should be conditioned prior to use to remove residual solvents from the polymerization process. This is called as conditioning of a GC column. And this conditioning of GC column is true for all types of GC columns. What it means is that you buy a column from the market, right? You connect it, you put it in the oven, but don't connect the other end of the column to the detector. Don't do that. And heat that column, let us say the range is 200, 250 as it is mentioned here. Keep it for some time so that the residual solvents in Chromatography or the other volatile liquids in other liquid coated columns are removed. And once they are removed, so the nitrogen flow continues. But instead of those volatile and other impurities being entering into the detector, they are just vented out. Once this is done, the column is said to be conditioned. And it is only the conditioned column, then you connect the other end to the detector and use that column for chromatography, gas chromatography separation. So what is true for Chromatography is true for all the columns in gas chromatography to avoid any small bleeding which may be possible, or to avoid traces of the solvents which may be left over in preparing the stationary phase. Conditioning is a precondition. Now here water and hydrocarbons separate. Water in solvents, sulfur compounds, natural gas, and C1 to C4 alcohols. These are the main applications of Chromatography, and you see all the molecules being separated are not high molecular weight compounds. They are relatively small molecular weight compounds. Yes. The peak of solvent in the second picture is in fact coming after the elution of peak 1 and peak 4. You see, compound 1 and compound 4, right? What does it mean? It means the retention of those two solutes, 1 and 4, are in fact much lesser than the retention of the solvent peak. This solvent peak is nothing but a solvent in which you have dissolved your liquid solutes, or solvent in which you have dissolved your solid solutes. So it will come out first. But the two solutes in fact are less retained on the column or by the column than the solvent, peak 1 and peak 4. Next. This is an example of separation of highly polar, and this using Sp234 number, and the chemical composition is given. So we have a standardized column for mixture of polar solutes. So if you feel that your mixture is polar, you use this column. And if you want to change the column, well, with trial and error, you can find another suitable column first. Next. Similarly, example of separation of non-polar. Next. Separation of hydrocarbons, highly non-polar solutes, and therefore ready-made standardized columns are available. And look at this sharp peaks, and we were saying that the GC is very quick, and in all these chromatograms you will see maximum 30 or 35 minutes all the solutes, maybe 10, 15, all are completely beautifully separated. Go back. Each chromatogram at this stage you must understand that this information given on the left hand side, suppose it is absent, and I give you only this picture of beautifully separated peaks and what that sample is. Will it be of any use to you, or will it make any sense to you? So any chromatogram which you give must accompany the chromatographic condition for which the separation was or is being brought about. So the first thing that you have to mention is what is column, heart of chromatography. See, a column is given 100 meter long, capillary column, and still you see peaks are sharp, baseline separated, and the separation is in maximum 32 minutes, 17 solutes. Then catalog number for you to order the column if you want, that is there. Oven, 15 minutes at for 15 minutes at 25 degrees centigrade, and then to 50 degrees at the rate of 2 degrees centigrade per minute, and hold for 5 minutes. Its meaning is that you start your separation at 25 degrees, right? And then 50 degrees, you increase, go to 50 degrees at an increase of temperature at 2 degrees per minute. So it is temperature programming. And at 50, hold for 5 minutes, so that all the solutes, volatile solutes at 50 will be eluted. This is the meaning of that. Then you have carrier helium. This must have been done in Western countries where helium is available. And that is 22 centimeters per second, milliliters per second. 22, they are given in terms of length. 22 centimeters per second it moves, and at 35 degrees. Then detector is, full scale. AFS is, FS is full scale, attenuation full scale, and injection is 200 microliters split. 100:1. I explained to you in this split 100:1. You can have 50:1 or 200:1 in split mode of injection onto the capillary column. We will show that in the laboratory to make your idea. I can't bring that injection system in the class. So I repeat, column is given, length is given, the internal diameter is given 25 millimeters, and it is coated with 0.5 micrometer film inside the wall. So capillary open tubular column. Then oven kept 25 degrees, and then temperature increases at 2 degrees per minute up to 50, and at 50 it is kept on hold, that is at constant temperature for 5 minutes. Carrier is helium moving at that migration velocity, and then injection is 200 microliters. Now you'll ask me, what is the detector? But we have not come up to that stage, so I'll explain to you in the next lecture. See the detectors. Like we imagine hypothetical detectors in our general theory of chromatography, that it senses only the solute molecules and not the mobile phase, right? In gas chromatography, so you need detectors to detect the presence and quantitate the amount. Now, once sample is injected, it goes through the column, it is separated, and then at the end of the column, when solutes elute out of the column, you place a detector, suitable detector. Now the selection of a detector will depend upon sample molecular structure, its concentration, and the proper choice of detector along with the column can optimize the results for the investigator. It means that if I want to choose, let us say, from a group of 20 students, a class representative, now that my expectation of class representative, that class representative must be proactive, must gel with the group of 19 other students, and then create an environment where exchange of ideas can take place between teaching faculty and a group of students. I don't want a leader which is introvert. She or he keeps everything to himself, and there is no communication between the teaching faculty or even non-teaching faculty, which is important in the laboratory, and the group of students. So choice of detector has to match with the type of solutes which are present. And we are going to see now in this phase what are those detectors, what are their ways of functioning, how do they function, what are their limitations, and then what are their advantages, of course. Next one. Any detector has to have certain characteristic features. For example, yes, one by one. It must afford adequate selectivity. Selectivity means that for a particular group of compounds that must respond. Sensitivity, it should not be such that I have to inject 100 microliters, then only solutes will be detected. It should be such that even for few microliters, let us say 2 or 5 microliter sample, that should respond, that should detect, that should quantitate. So selectivity and sensitivity. Then there has to be a linear response of the detector over certain concentration range. I'm going to give you this presentation at the end of this lecture. Just as we copied the other one, you can copy this, the class representatives, right? Now the third is that it should give a linear response. Now when we construct a calibration graph, as you have seen, in colorimetry or in chromatography we have said, what we do, we take different concentrations, x to 10x, let us say, 10 samples, and measure certain property under given conditions and plot a graph of concentration as a result of the response. You get a linear curve. And that linear curve is not linear over a very, very wide range of concentrations. It has its own limits. But if these concentration limits are practically useful to us, very nice. So this detector that you will choose for your solutes must be such that for X concentration, if it gives 10 units of response, then for 2x it must give 19 or 20 or 21, approximately twice. And for 10-fold, it has to give approximately 10-fold response. Then we can say that yes, the detector response is linear in the concentration range of, let us say, 1 microgram to 10 microgram, or 1 microgram to 50 microgram, whatever. You have to establish that linearity. But the detector must give linear response within certain concentration range. At this stage, let me make one point very clear. That for a given set of solutes in the sample, there may be 10 different solutes, let us say. and 10 different solutes are different molecules. And it is not necessary, therefore, that a given detector will give the same response to all the 10 molecules. What I mean is that you are a group of 80, 90 students. I can't expect everyone to receive my lecture exactly with the same intensity. It's not possible. So detector is also a poor thing like us only. So it tries to give response, a linear response for all 10 solutes, but if the concentrations are, let us say, equal of all 10 solutes, it may not give the same response for all 10 solutes. Then you say, how do we do? Well, if you are doing a rough estimate of the percentages of these solutes in a mixture, there is a process of normalization. What is done is, the response of all these 3 detectors is 100, let us say. And therefore, response of each one is X units. So what is the detector response for X? So through this process of normalization, we can approximately find out what is the detector response for each solute in a mixture. But don't expect always that the same detector will have the same response for the same concentration of different solutes. That is the point I want to drive home. Next. So a temperature range from room temperature to at least 400 degrees, but above 250 requires specialized stationary phases. Up to 250, yes. Higher reliability and ease of use, yes. And a short response time that is independent of flow rate. My flow rate of mobile phase may vary. I may put 10 milliliters per minute or maybe 50. The response should not be dependent on the flow rate of the carrier gas, number one. And it should be very fast. Any Sardarji here? Don't take any office. But like that Sardarjis normally give response relatively late. That is the joke of the society, which is not true, because my principal is much, much brighter than me in terms of response and intelligence. So I have that example. But what I mean is, the solute enters the detector and then detector then detects. That will not do. Instantaneous detection. And that is what is our last point. That last one. Short response time. It should be very short, in microseconds. And similarity in response towards all solutes is ideal expectation, which I explained that it is not ideal situation, never exists in this world. We try to achieve that, but it never reaches. And non-destructive to solutes, so that solutes can be recovered after separation. And noise and minimum detectable quantity. We'll see what is noise, and then we'll see what is the detection limit, lower detection limit in the next few slides. Now there are some detectors which are classified as, I'm sorry, those read this thing, integrating or differentiating detectors. But we'll not go into the details of that. We can skip these slides. We'll go to the detectors straight away. Go ahead. Next, because we have seen this AUC versus concentration and how the area under the curve is calculated. Next. Go ahead. Skip this. Yes. Now whenever you record your chromatogram, there is inherent noise on the baseline. Generally you will not get very stable baseline. Some minor disturbances inherent are there, that is called noise. Now here we have shown the basic noise is 1N noise, and twice of that is the lower detection limit. So if somebody asks you what is the lowest detection limit of your detector, well, it is twice the N. So anything less than 2N is not acceptable as a detector response. So minimum 2N and above. So N is the noise inherently associated with almost all chromatograms. It can be minimized but cannot be eliminated. So you find out first what is the noise level by running a blank without any sample. And then lowest detection limit of that detector will be twice the N. And that is very important for you, because otherwise the noise can be mistaken sometimes for a response to the component. Next. Linear relation, which I have explained. Linear range of a detector may be defined as the ratio of the largest to the smallest concentration within which the detector is linear. Say 2 to 50, 2 to 10, 2 to 20 micrograms of solute. We will see these 5 detectors and their functioning very carefully. Thermal conductivity detector, flame ionization detector, electron capture detector, helium ionization detector, and nitrogen phosphorus detector as main detectors being used in gas chromatography. You will ask me, are they the only detectors? No, there are many more. But from our point of view, these 5 will suffice. Correct. Hold it. First, we will consider TCD, thermal conductivity detector. Do you remember that in one table I have given you thermal conductivities of different carrier gases, right? And they were different. Some were very high and some were very low. Now the basic principle on which this TCD works has to be understood very carefully. You don't have to draw these figures anywhere in examination also, but you have to understand. It's a Wheatstone bridge if you see, right? Now, when at a given temperature, only the carrier gas passes through the detector, it will have certain, it's a balanced Wheatstone bridge, no imbalance between two. Now the moment the carrier gas enters with solutes, one segment continuously gets only carrier gas, and the second segment now gets carrier gas plus solute. Now the thermal conductivity of only carrier gas and thermal conductivity of carrier gas plus solute is bound to be different, depending on thermal conductivity of the solute. And this difference is the signal. This difference is the signal which can be used for qualitative as well as quantitative analysis, because this difference is proportional to the amount of solute flowing through the carrier gas. Carrier gas has certain fixed thermal conductivity under given condition. Carrier gas plus solute there is a difference. Western breach is disturbed, unbalanced, and to balance it, then it is automatically done and signal is generated. Then the second solute comes. It may not have the same thermal conductivity as the first ones, but then there is change. And second solute is detected, and the 10th solute, and so on and so forth. Now, so in thermal conductivity detector, it is expected that the thermal conductivity of carrier gas and thermal conductivity of the solute must have large difference to create a large signal for even small concentrations. Now, when we see that, we will always be tempted to choose helium as a carrier gas because its thermal conductivity is very low, and solute it will be high, and therefore difference will be high, but then helium we cannot afford. So what is the next phase? Maybe argon, it's also that, not that cheap, and then come to nitrogen. Nitrogen is freely available, it's cost effective, but its thermal conductivity is very high. They say fine, it's okay, as long as it does the job of detection using TCD, we are happy. So when you use thermal conductivity detector, it takes time for thermal conductivity detector to stabilize. It takes time. So what are the advantages of TCD? One advantage is that it responds to all types of solutes irrespective of its nature, whether it's polar, non-polar, whether it is an amine, an alcohol, aldehyde, ketone, or inorganic complex. It means it is a universal detector. Universal detector. It does not respond to only a specific type of compounds. So TCD is a universal detector, but it takes time for stabilization, and then its sensitivity is not very high when we compare with the other detectors. Okay, so one by one. That measures the thermal conductivity of the analyte in a carrier gas compared to the thermal conductivity of the pure carrier gas. That's what it is. TCD works proportionally to the concentration. Since TCD reacts non-specifically, it can be used universally for the detection of both organic and inorganic substances. So it's a universal detector. Helium or hydrogen, as thermal conductivities of hydrogen and helium are approximately 6 to 10 times higher for organic compounds. Non-destructive, of course, the TCD, and sensitivity is only ppm. Compared to other detectors, we'll see it is ppb, ppt also. Next. Yeah. Picture, please. This is one of the most common detectors used in gas chromatography. It is called flame ionization detector, FID. You must be remembering that table in which I have given auxiliary gases, oxygen and air. Now here is the application of oxygen or air gas. A very hot flame, you know your Bunsen burner, it's like micro Bunsen burner there at the center of the, you see the flame tip. So hydrogen gas and oxygen or air, most of the time it is air, in the ratio of 1:50. 1 part of hydrogen, 50 parts of air is mixed and burned at the tip of a microburner to create a very, very hot flame. So that is the name of the detector's flame. That is the reason we need auxiliary gases like hydrogen and air or oxygen to create a hot flame. So here hydrogen is not used as a carrier gas. Hydrogen is used to create a flame, hot flame, when it burns with air. Now the temperature is very high, 1500, 1600 degrees Celsius. And your solute molecules enter the burner from the bottom and then reach the tip of the burner where they get combusted. And when combustion takes place, positive ions are generated. And the number of positive ions generated depends on the number of carbon atoms present in the organic molecule is being taken to the flame. I'll explain again. In this, in FID, flame ionization detector, a very hot flame is created by mixing hydrogen and air or hydrogen and oxygen at the tip of a microburner. When solutes move through the burner on the top of the in the flame, they are all combusted. Positive ions are generated, and the number of such ions generated depend on the number of carbon atoms present in an organic molecule. And naturally, there are collector electrodes, if you see in the graph in the picture, and a current is generated, and that signal in terms of the current generated is proportional to the number of ions, and we know number of ions is proportional to the number of carbon atoms present. Now here, the disadvantage is that it is a destructive method of detection. When you introduce the sample is burned out. So this is one disadvantage associated with FID. What is the other disadvantage? The other disadvantage is it is used for only organic compounds. Now will it be therefore universal detector? What will you call it? A specific detector, specific to organics. But the other advantage is that its sensitivity is very, very high. And therefore, where recovery of your solutes is not important, it's only the qualitative detection and quantitation of solutes is important, FID is the detector of choice. So the detection principle is based on the change in the electrical conductivity of hydrogen flame in an electrical field when feeding organic compounds. The organic compounds escaping from the separation column are pyrolyzed or burned. During subsequent oxidation by oxygen, which is fed into the flame from outside, ions are formed by the following reactions, and the flow of ions is reacted as a voltage drop across the collector electrodes, generating the signal. See, have a look at the picture. So the gas flow from column at the bottom of the flame, bottom of the burner, you see, it goes through that. Now, air inlet is from 1 and hydrogen gas is from 1, and it is mixed with air and then burned at the top of the burner. There's a very interesting story of this, which you like, I am sure you'll enjoy. And I was one of the witnesses there of this. Although in the world commercial gas chromatograph was introduced in 1960, in India, we used to import all these GC instruments. And simultaneously, in late 60s and earlier 70s, development of indigenous gas chromatograph was undertaken by a group of BARC scientists. And I was there undergoing their training, and I was there for a witness. I was not part of this development. And this GC was being developed under the guidance of one scientist, Dr. R.M. Iyer. He's still alive. He's 80 plus now. Recently I met him. After struggle of few years in 1971, yes, this was ready. And with all fan and fair, they invited the director of BARC to inaugurate the first indigenous GC, which was in collaboration with Toshniwal. Toshniwal is a group of people in dealing with sale of instruments. So Toshniwal had sponsored that project. So Toshniwal higher officials were there, and director came, and everybody was anxious, and they injected the sample, and the signal will not be detected. Everybody think what is happening. Second time they injected, nothing happened. The chart, there used to be chart paper to record. Nothing happened. And it was very embarrassing situation for R.M. Iyer and his group, and of course for a young person like me, they understand it, that if such big persons are there and the gas chromatograph is not working. And after a few minutes of this struggle, R.M. Iyer suddenly realized that he has forgotten to lit the flame. Without the flame, how can there be burning and the detection? And the burner was not electronic burner that time, match. And the burner was lit, sample was injected, chromatogram came, everybody flew. But such embarrassing situations are always there in all research projects. We research guys expect something to happen, and on that very precious moment, many times things don't happen, and we are embarrassed. There are few occasions like this, but then Dr. R.M. Iyer has to be credited to have first indigenous GC, and then the technology was transferred to them, and now in India there are at least half a dozen of manufacturers of gas chromatograph. So this is how I remember from FID. Go to the earlier slide. Earlier. Yes. Electron capture. So we have in this detector a rich source of free electrons generated by a source of radiation. A radiation source is there which emits electrons, beta particles, right? And there is a constant concentration of electrons inside that chamber. Now when a solute enters into that, and if it has ability to capture electron, certain number of electrons will be captured depending on how many solute molecules are entering into that. And therefore, the density of electron earlier and the density of electron after the solute enters will be different as a result of electron capturing by the solute molecules. Signal is generated, and therefore electron capture detector, is it universal? It is only specific to those solute molecules which can capture electrons, which are electronegative. Is it not? Is it? Which have ability to capture electron. Easiest way to remember that. And if that can happen, only then the detector can be used effectively. Next. Yeah. Now this is flame emission detector. You have seen, you have worked on flame photometer? No? No, Ruites, sorry, calcites, police, we have a flame photometer. Please use that for the detection and quantitation of sodium, potassium, calcium, magnesium. So group 1 and group 2 metals. In flame photometer, what happens is regular Bunsen, right? And an aqueous solution of that is fed to the burner, let us say sodium. At that temperature of the flame, there is excitation of electrons from sodium, and the electrons come down and emit certain amount of light. Yellow flame test you must have conducted for sodium, it's nothing but that. Or scarlet red for potassium, or calcium, brick red. Now those flame colors are because thermally these atoms are excited, and in excited state they cannot remain stable for a long time. So electron 10, it is used for quantitative and quantitative determination of sodium, potassium from various matters. It can be from urine, it can be from blood, it can be from water, whatever. Now this is similar to that. So flame emission is a very simple thing. There is a flame, very hot flame, and certain emission, and that emitted energy is measured, and the detection and quantitation is so sensitive, but it is again a specific detector. It's not universal detector because it is specific to those which can be excited and which will emit light which can be measured. Next. See, specific property of detector is selective to phosphorus and sulfur and sensitive to 2 parts per trillion. So where is the application of this detector? Application of this detector is in the trace level detection of insecticides, pesticides which contain phosphorus and sulfur atoms. So residues from different samples like food sample or water sample, effluent, can be done very effectively at very low concentration because it's highly sensitive, but then specific in nature, not universal in nature. Specific to those containing phosphorus and sulfur atoms in the molecule. Next. So, if you compare these detectors, then there is a linear range which we have understood. The linear range is highest for FID, but others also, not that. Detection limit, let us see, ECD non-specific, 10 raised to minus 8 grams. FID, 10 raised to minus 13. ECD, 5 into 10 raised to minus 14. Phosphorus and nitrogen, and phosphorus and sulfur, 10 raised to minus 15, 10 raised to minus 14, and 10 raised to minus 11. So they are all highly sensitive, FPD, PID, ECD, FID, except that they are non-specific. ECD is not that sensitive, but it has great advantage of being useful for all molecules. It doesn't, no discrimination between SC and ST and open category, no discrimination. Whomsoever is accommodated, like our college. No discrimination between Maharashtrians and South Indians and North Indians and SC and ST. Everybody is accommodated, giving the same treatment. But then we are poor, not very rich. Okay. Next. Data systems. These days you know that you don't have to record a strip chart, chromatogram and strip chart recorder. You have integrators, and then personal computer also can be connected to control all the systems of GC. Okay, we'll take a 5 minutes break here and then come back and say something about the limitations of GC. We'll first find some applications and then we also will discuss limitations, because unless we understand limitations, we cannot understand the importance of GC and importance of other aspects. Diagram we saw on the first day. We have presented all the components of it, the approved, the detector and the product. Now the basic question is, it's fine that you can use GC for analysis, but given a sample in a particular matrix, matrix means it could be in the form of a powder or a solution or a blood sample or any other biological sample, anything. You have to prepare a sample for introduction into the GC. So that sample preparation is very, very important step for any analyst doing gas chromatography separation. Nobody is going to give you in hand ready-made sample to be introduced into GC. Now when you prepare a sample, you have to be very cautious about the safety, your own safety and safety in the laboratory. Because again, you will not be always lucky to get non-hazardous sample. There may be hazardous samples also. How to tackle these hazardous samples and how to extract the components that you would like to analyze by GC is also extremely important as an analyst working in the laboratory. So safety aspects of sample preparation, according to me, is more important than the analysis itself. Because you have prepared everything now. You have selected the right column, you have selected the right temperature conditions, flow, you have selected the carrier gas, its flow rate, everything is standardized. But now it comes the real sample analysis, real sample analysis. So that is how we see it. For analytical results to have any validity or meaning, adequate sampling procedures should. See, when a sample comes to you, it is analytical sample for analysis. But how is that analytical sample prepared? Let us assume that in the store 10 drums of solvents are received and you are asked to find out whether these 10 drums contain the right type of material in the right quantity. So since they are all liquids, we say from 3 parts, upper, middle and lower part of the drum, each drum, there are sampling devices. So with the help of sampling devices, a person who is trained to sample will withdraw from all 10 drums, mix all the 10 drums sample, and that is a gross sample. So where all the 10 drums are represented. Now from that gross sample, a small amount will be, because if it's a homogeneous liquid, the sampling becomes relatively easy. So from that a small portion will be for analysis, maybe in small bottle. It will come to you in the laboratory. You are supposed to do the GC analysis. And the GC analysis that you give in terms of qualitative and quantitative aspects will be representative of all the train drops. Okay? Then that is what is important. That analytical sample must be representative of the bulk material received in the stores. Otherwise, you sample only from one drum, only from the top layer, it may be misleading. And so, sampling in industry, chemical industry, pharmaceutical industry of raw materials is as important, or sometimes according to me, more important than the analysis itself. And that is, and every analyst in the industry is circulated in all sections, that I will discuss sometime later. So every analyst at the end of maybe 1 or 2 or 3 years has to become expert in sampling, in chemical analysis, in spectroscopic analysis, chromatographic analysis, method development. Then only you can jump to the next step. Otherwise, you are not there. So today, just we'll briefly understand why sampling and how sampling. Yeah. See, it is process of extracting from large quantity of material a small portion which is truly representative. Yes. The sampling process involves several steps depending on the nature of the sample. If necessary, alteration of physical state of the sample, that is, that can be manipulated. For example, you have 10 wagons of coal received. Now you know the coal materials, coal is a heterogeneous in terms of size. Some are big lumps of coal, some are small lumps, small powder. If you see the wagons of coal received by power station, where power is generated. So for such heterogeneous material, you sample according to the procedure given specifically for that. And then once you receive, you cross sample, you have to powder it. So you have to convert it into a powder of uniform particle size before you can send an analytical sample to the lab. So it's not that always you can directly send the sample to the laboratory, but you have to do some process of converting that material into suitable form to be analyzed in the laboratory. Yes. Then transportation to the laboratory, storage prior to analysis. This is very important for storage, because if you are doing sample today and want to spend sample maybe after few days to the laboratory, because laboratory is very busy, and if it contains volatile components, you must store under packed, cool condition. Otherwise, the volatiles will get evaporated, and the analysis that you will get subsequently may not be the true analysis representative of the sample. And introduction of the sample on the DE. Hazardous, as I said, that analysts must, as a general rule, try to obtain the prior knowledge of the material he is expected to analyze. So history of sample, as I said. Just because your boss tells you to analyze this by GC, you must first ask, what is the nature? Is this highly highly inflammable? Is it easy to handle without gloves? But to be on the safer side, always in the laboratory, you have to wear safety glasses and always wear gloves so that you don't come in direct contact with the material, which may be irritating to eyes, irritating to skin, irritating for inhalation, etc. etc. Yes. Next. So no naked flame should be allowed near sample area if the sample is known to contain inflammable components. Suppose you are evaporating ether when you do solvent extraction. Normally you evaporate ether. Now when you evaporate ether, it has to be evaporated on the water bath, and no flame should be around. Otherwise there will be flame in the entire lab. Then pressure changes may release excessive quantity of gas sometimes. You can skip this. Next. Sample size. What should be the sample size? Sample size will be guided by what do you want to analyze from that sample. Because a cold sample, for example, in a cold sample, if you want to analyze what are the volatiles there, then the size of coal may be 1 kilogram given to you. And the sample to be analyzed volatiles from them, it may be in microgram or milligram level. And therefore, size will be decided by, size of the sample will be decided by what is the quantity of the solute to be analyzed in that sample. In the case of gases, it is common practice to vary the amount of sample by introducing different volumes at a constant pressure. And the sample size will obviously be related to the kind of solute, stationary phase interaction, and consequently to the shape of the final chromatographic phase. What are the main applications of GC? Plenty of applications in qualitative as well as in quantitative analysis. Next. What? These are different techniques you have to resort to in gas chromatography. It's not always that a sample is given and you inject into them. It's not that easy always. So, for example, chemical derivatization is sometimes required because you have a sample to be analyzed, a fatty acid for example, long chain fatty acid. It's very difficult to vaporize. So you convert that into silinated derivative. So there are derivatives, methods, and those derivatives then become volatile. And you analyze the fatty acids in terms of the derivatives that you prepare. So derivatization many times is a prerequisite for such type of solutes to be analyzed by gas. In fact, I was going to discuss this along with the limitations of GC, but now that the pyrolysis part has come, I would like to discuss. See, one of the drawbacks of GC is that non-volatile solutes cannot be analyzed, and secondly, those solutes which are thermally labile, that they undergo decomposition, generally are not suitable for gas chromatographic analysis. But there is a method. If you can establish that under a given experimental conditions of temperature, your solute gives reproducible decomposition products. That suppose at 150 I heat A solute, it gives A plus B plus C plus D only solutes all the time, decomposition products. Then I can still analyze that sample by decomposing it at that temperature and analyze its quantity in terms of its decomposition products. This is called as pyrolysis GC. So there is a unit to pyrolyze the sample, put the vapors onto the GC and do the analysis. So actually this is thermally labile solute. But since this thermally labile solute gives me reproducible decomposition products, I am in a position to do qualitative, I am able to do quantitative analysis in terms of its decomposition product. That is called as pyrolysis gas chromatography. Next. See here. Okay, you can skip. Quantitative analysis is an integral part of GC, where you want to find out the concentration of each solute in a sample. Three methods are there: area normalization method, which I described you, your internal standardization method, and comparison method. Let us see first area normalization method. Next. Yes. What is done here? That there are 10 peaks. The areas of all 10 peaks are calculated, and the, let us say, area is X. Then that area of your peak divided by the total area of all the peaks multiplied by 100 is the percentage of your solute in the mixture. So it is normalization irrespective of the fact whether the detector gives equal response to all the solutes for the same concentration or not. We measure the areas of all the peaks, take a sum of that. So then let us say I want to analyze the first peak concentration. I say area of that divided by total area into 100 is the percentage of A in my mixture. So B in my mixture. So this is a very common method, area normalization. Internal standardization. Now please don't look at the slide. I'll explain to you. Let us say you want to analyze Vicks Vapora. It contains volatiles. Otherwise you will not get that soothing effect. That typical aroma is because of the volatiles. And you are given that sample. Now it is in the form of a, what is that, paste? Huh? Gel. It is gel. So from that gel, you have to extract the volatiles in a given solvent. It may not be possible in just single extraction. So maybe 3 extractions in alcohol. You take 10 grams, first extract with 25 ml, filter, another 25 ml, third time to ensure complete extraction. And then put it in one volumetric flask and dilute it back to the mark, let us say 200. So you know 10 grams and the volatiles are now there in the 100 milliliters of alcohol. You eject the sample and find out the solutes through retention times and from calibration graph of each peak previously done, you quantitate. But in such analysis, there are errors involved because you are doing in 3 steps. There are errors involved in weighing, errors involved in dissolving and extracting in the solvent, and therefore these errors will be reflected in quantitation especially, not in quantitative analysis. In order to avoid that, what I do, when I weigh 10 grams of jelly, I add a fixed quantity of structurally similar compound in that jelly. Mix it and then extract the mixture. Because that compound which I have added from outside is structurally similar, it is expected to be extracted also the same way in the given solvent. I prepare 100 milliliters of that. Now when I inject certain quantity, 5 microliters, 10, 15, etc., the error is minimized because I don't measure now the area of only the solutes present in the jelly, but sidewise I also measure the area of that internal standard which I have added. And I plot a graph of the ratio of the area of the peak to the area of the internal standard versus the concentration of my solute, not area of the solute versus the concentration. So even if there are errors in extraction of main solutes, they will be reflected in the area of extraction of the internal standard as well. And I am taking now for construction of my calibration graph the ratio of the area of my solute to the area of internal standard, and then plotting that ratio versus concentration of the solutes of interest, and that will minimize my error in quantitation. This method is known as internal standard method, addition of internal standard, especially in biological analysis where the concentrations are so low of the metabolites and unmetabolized drugs. You have to choose a proper internal standard to compensate for the errors of extraction and for errors of injection. And that reduces, that doesn't eliminate, but that reduces considerably the procedure of quantitative analysis. Now the third method is comparison. You have a certain thing, standard, you compare with the sample. So third method, the next one which we have mentioned in quantitative analysis, is comparison. In this method, a synthetic mixture containing known quantities of the components of interest in the range of concentration expected in the unknown sample is prepared and analyzed. Synthetic known. And then the values of the peak areas for different known volumes of synthetic blends are estimated and calibration graph is plotted. An exact quantity of the unknown sample is then taken and injected and compared with the standard. So it is a comparative method. No internal standard is added yet. Only synthetic sample is prepared first of standards, and that concentration in terms of area under the curve of the sample is compared for quantitative analysis. Yes. Now we have GC analysis for bacterial identification. Let us see. Microbiological analysis, then environmental analysis, then water analysis, air analysis, clinical and toxicological analysis, forensic toxicology. So what we say, versatility of GC is also reflected here, that you are in a position to analyze solutes from different samples of different nature. Long chain fatty acids found in the bacterial cell can be used to distinguish between various microorganisms. See, here we are not directly measuring the bacterial count or say, but take advantage of the long chain fatty acids. And each bacteria will have differences in the fatty acid and the type of fatty acid, the quantity of fatty acids. And once you standardize for, let us say, 100 bacteria, you are given a sample, you separate the fatty acid, find out, and by comparison, you can say which bacteria must be there given to you for analysis. Next. Water analysis is very common because of the organic pollutants, and you will use FID, obviously. air analysis also, organic vapors, again using FID. Next, clinical toxicological analysis. The analysis of lidocaine was done using flame analysis. Lidocaine is a local anesthetic. If you have great pain, apply the paste cream of lidocaine immediately. That subsides, pain subsides because there is numbness. Have you gone to dentist? Never? What injection he gives? Lidocaine. It's a local anesthesia. The effect lasts for 2 hours. So you are not supposed to eat, otherwise you will chew your tongue. And that is to avoid that. The dentists always say, don't eat for 2 hours. So that sensation goes, and then you eat. That is lidocaine. So lidocaine can be analyzed again by GC using FID as the detector. Next. Forensic toxicology. See, analysis of toxicants in normal samples and from forensic samples is not very different. Only the way the samples are collected by forensic scientists is different. Mostly they are from dead bodies. DNA sequencing is one thing, but other poisonous substances that are found in the stomach or in the other parts of the body, they can be extracted and determined by gas chromatography. Yes. That's the end. That's this slide. 104. Close your eyes. I will summarize in 5 minutes what we have discussed so far in GC. We started again with the definition of gas chromatography, which we had learned earlier in the general theory of chromatography separation. And we said it is that method of separation in which mobile phase is gas and the solutes being separated are also in the gaseous state. It can be gas solid chromatography or gas liquid chromatography, depending on whether the stationary phase is a solid or a liquid coated on an inert solid surface. We said that till 1939, all separations were being conducted only in liquid chromatographic mode, TLC, paper, column, etc. When Martin and James published for the first time possibility of separating solutes in the gaseous phase, there was a lot of excitement among the researchers who were interested in separating solutes in the gaseous state. So, from their finding in 1941, in less than 20 years, first gas chromatograph came in the market, commercial gas chromatograph came into market. So was the excitement. And then we say, why this excitement was there? The excitement was there because of certain attributes of GC. That GC analysis was very fast, complete in about 30 or less than 30 minutes. It was very sensitive method, being able to detect solutes in parts per million to parts per trillion level. It was inexpensive relatively. Then sample size was very small in microliters, non-destructive in most of the cases, and highly versatile in nature because GC could separate mixture of gases, mixtures of liquids, mixtures of solids also by using suitable experimental conditions. Then we saw a normal block diagram of a GC, and on our left side was a cylinder of carrier gas with all the attachments to control the flow and the flow, reproducibility of flow. There is a compressed gas like nitrogen or hydrogen or helium or argon placed in the cylinder that is carrier gas. And we say carrier gas has to be inert, free from impurities, free from moisture. And its role in gas chromatography is just to take the solutes from one end of the column to the other end of the column. Carrier gas in gas chromatography does not play any role in the separation of solutes. So in the separation of solutes, only the stationary phase plays a role, which could be an adsorbent or which could be a liquid coated on an inert surface of stationary phase. Then we saw the injection port, where the sample is introduced through a self-sealing Teflon septum. The volume of the injection port is very small, so that the moment the solvent and the solutes are evaporated instantaneously at the temperature of the injection port, all solutes and the solvent vapors enter into the column simultaneously in one plug. That's why its volume has to be very, very low. Its construction material has to be inert so that no chemical reactions take place. And its temperature is fixed at certain value, which is electronically controlled within a very small range, plus minus 0.1 degrees Celsius. It is electronically independently controlled. The temperature of the oven depends on the volatility of the solutes we are introducing into it. It could range from room temperature up to 400 degrees Celsius. From the injection port, it goes onto the column, which is kept inside an oven at the same temperature as that of the injection port, so that there is no condensation of vapors on the column. So separation takes place there, and then solutes are eluted from the other end of the column and are detected by either universal or specific detectors. Now the liquid stationary phases that you can choose should be such that they should dissolve the solutes completely and bring about separation. So they should be good solvent for all the solutes. They should be thermally stable, so that at operating temperature they should have minimum vapor pressure. And then the liquid phase loading could vary between 2 and 20%. You have a choice for non-polar solutes, stationary phase, polar, and some specific stationary phases like chiral or high temperature withstanding liquid stationary phases. Columns are generally packed columns or capillary columns. Packed columns have a higher diameter and they are made up of stainless steel in the form of a coil. The capillary columns, or open tubular columns as they are called, are made up of fused silica, and the inner wall of these columns are coated with suitable liquid, the middle section being an open tube, and therefore they are called open tubular columns. Their length varies from anything from 20 meters to maybe 100 meters, but because of their narrow bore, the column separation efficiency high, and also the time of separation is relatively low. They are used, capillary columns are generally used in the separation of volatile solutes having very close boiling points. And the main area of their application is petroleum industry. There are other applications of capillary columns as well. When it comes to detectors, we saw that mainly thermal conductivity detector is a universal detector, but its sensitivity is low. Flame ionization detector is specific to organic solutes, can detect solute up to ppm level, whereas the electronic capture detector and flame ionization detector specific for phosphorus and sulfur atoms. They are highly sensitive and they can detect solute concentrations in parts per trillion level. They have specific applications, and therefore using detectors, an appropriate detector for appropriate sample, it is possible to do analysis of gases, analysis of liquid mixtures, analysis of solid mixtures as well. Then we saw how to prepare a sample for GC analysis and what precautions need to be taken for hazardous samples. So there are various ways of preparing a sample by extraction and different procedures. Then there are methods of qualitative and quantitative analysis. And for quantitative analysis, you can have area normalization method or internal standard method or comparative method. And GC has a wide number of applications in diverse fields like environmental, like toxicology, like forensic science, and also in biological analysis and normal pharmaceutical analysis also. So thus, gas chromatography is a very popular technique of separation, but then it has also certain limitations. Their limitations are in terms of the fact that only thermally stable and volatile solutes under experimental condition can be separated and analyzed. Non-volatile solutes and highly thermally labile solutes cannot be analyzed. And therefore, biological samples like blood, urine, saliva, they are not suitable candidates for analysis by GC unless, of course, we extract the desired volatile components from them by solvent extraction and resort to gas chromatographic analysis. There are some methods where thermally labile compounds also can be analyzed by GC, provided that under temperature conditions mentioned, that thermally labile solute gives reproducible decomposition products. If it is established, then we can analyze quantitatively such thermally labile solutes by using what is known as pyrolysis gas chromatography. And pyrolysis gas chromatography is a special application of gas chromatography. So when we understand the merits of any analytical methods, we have to also appreciate and mention the limitation of that method, so that when a sample comes to us, we can understand whether or not gas chromatographic analysis can be useful for that sample. Thank you. Alles heard or some more? Huh? Right. I think we'll take a break because I want to start a new, totally new and very interesting topic for 3 days, last 3 days. Last Saturday 1 hour test, and I want every one of you to write precise and crisp answers, not vague answers. It's a part of internal assessment, and I assure you, as an examiner, those vague answers will be treated very harshly. Harshly, H-A-R-S-H-L-Y, harshly. Otherwise someone will say, what you said, we have not heard of. But then you have to be a good listener in future and sharp answer. Correct? So far we have completed theory of chromatographic separation and theory and instrumentation and applications of gas chromatography. But still interesting remains to be studied next 2.5 days. क्लेम्स कराना तैयार नहीं तुम क्या आपका ही है? हाँ? क्लेम करता होगा